Welcome to the Plant Services Podcast series, The Hidden Costs of Compressed Air, sponsored by Kaeser Compressors. Each podcast in this 4-episode series tackles one of the many facets of compressed air system operation and costing. I'm Tom Welp, the Chief Editor of Plant Services, and today I'm joined by two compressed air experts from Kaeser, Neil Meltretter and Justin Aycock, for a discussion on the hidden costs of air quality that can be associated with your compressed air system. Neil is Technical Director for Kaeser Compressors and has conducted and supervised thousands of industrial compressed air studies to help plant teams achieve significant energy savings and operational improvements. And as Kaeser Compressors product engineer for air treatment, Justin is responsible for the technical sales support and education for Kaeser's extensive lines of air treatment product, including filters, dryers, drains, and condensate management. Welcome, guys. Thanks for being part of this special series.
Yeah, thanks for having us, Tom.
Yeah, it's a pleasure to be back, Tom.
Well, I can't wait to get started on the air quality discussion. Justin, I can fire a question at you first. Let's get right into the topic of standards for air quality. Can you talk to our listeners about some of the common methods that are used to treat compressed air to meet required ISO classes?
Yeah, sure, Tom. But I think first we need to define what the ISO classes are for. The classes are for classifying filtration and drying methods with respect to the big three contaminants for compressed air: particulates, water, and oil. It can be very difficult to replicate or meet these ISO classes in the field because drying and filtration equipment are tested to a standard, ISO 7183 for dryers and ISO 12500 for filters. And the standard test conditions will not be the same as the conditions in the field. So the challenge the air treatment equipment can see is very different for every installation. You can compare this to installing a system in a pharmaceutical plant versus a cement plant. The cement plant is going to be obviously very dirty and a lot more contaminants than a pharmaceutical plant. You also got to remember the compressor ingests ambient air, and the ambient can change depending on the installation of the equipment, where it's at. So the ISO classes are just classes, a way to classify and certify equipment. And it's kind of very difficult to guarantee how the equipment will operate in the field to the classes to an exact point. So with that being said, you can have an air treatment system with multiple equipment and try to have the best insurance policy close to the ISO class so you can have the correct quality air and then the best product and whatever you're using with the air. So for example, if you want an ISO class 1.1.1, you would use a high efficiency pre-filter to a desiccant dryer that's capable of reaching a minus 94 degree F dew point, then a particulate and adsorption filter after the dryer to give you the best air quality possible. So that would give you the best air quality with the most equipment. So it would obviously be the most expensive. So if you had less stringent requirements, you would use less equipment or just different equipment. So like a refrigerated dryer instead of a desiccant dryer, and that would definitely be a lot cheaper. So determining your ISO classes can help you choose the correct equipment and reduce your cost.
Okay, those are great points. I'm curious, Neil, do you have specific application examples that you can share with us?
Yeah, Justin gave us some great how-to. And then we talked really about the standards on how to get to what is really required. But most customers see this as what's the application? So is this a food application, incidental contact? Are we packaging something? Or it could also be, let's say, a paint application where you're very concerned with condensate, water, oil, etc. That's getting the line. And that's how you decide which type of air treatment you need. Do you need a dryer? What kind of dryer is that? Is it a refrigerated dryer, which is nominally 38, 40 degree pressure dew point, or is it a desiccant dryer, which would be 0 degree Fahrenheit pressure dew point or lower? Most folks run at minus 40 degree pressure dew point with those desiccant dryers, and then you'll need the filtration associated with it. So it really runs the gambit on what's required for each application. And that's the great part about being in this business is even when you do talk to the same customers, you don't see the same things.
So Justin, sounds like it's possible to have too little air treatment in your system. So let me ask about the possibility of too much air treatment. Can you have too many dryers or filters? Like at some point, does extra treatment do more harm than it does good?
Oh, yeah, definitely. You can have too much treatment. I mean, it would be a problem just for your operating costs and also your initial costs. Like if you're just kind of like a general plant, you only need ISO class 4 for water content, but you have a desiccant dryer, you're going to have a much higher operating cost as, having a desiccant dryer, you're using your process air to regenerate the desiccant bed, and that process air is very expensive to make. So the capital cost and also the capital cost of the desiccant dryer is higher. So you kind of have two facets there, operating cost and your initial cost, which is going to play both into having higher operating costs by having more air treatment, and you don't really need that. And it also plays into pressure drop too. If you have too many filters in different places when you actually really don't need that many filters to meet your air requirement, you're going to have a higher pressure drop, and that pressure drop is going to coincide with a higher energy usage in your compressor. So there's also an issue with oversizing dryers. So if a dryer is oversized and you don't have any energy saving methods, you're missing out on opportunities to save a little bit of money. So for example, if you have a system that only needs 100 SCFM of air, but you have a dryer that's rated for 200 SCFM, after applying all the correction factors, and the dryer is non-cycling, then you're going to be using that dryer flat out. It's just going to keep running. But if you had an energy saving dryer, like a cycling dryer, then it would just cycle on and off, depending on the demand. So then you could potentially save up to 50% because if the dryer is rated for 200, but you only need 100 SCFM of air, then that's about 50% of energy savings that you could have. And this would also be the same for sizing desiccant dryers and membrane dryers, and even more so because they use purge air, which is, again, like I said, it's inefficient and costs a lot of money to generate. So sizing your system, sizing your air treatment equipment for the system will give you good money-saving benefits.
I absolutely agree. Justin had some really fine points in there. I think, it's a hard question to answer because, you do talk to customers who are very conscientious about meeting a specific either pressure dew point or ensuring they don't have any water in the lines. And we do run into customers who, instead of putting all their refrigerated dryers in parallel, they might put two large dryers, one in series with the other. And, so like Justin said, if you have a hot gas bypass valve dryer, which is running fully loaded all the time, and you don't have any energy saving potential for that dryer, you're really missing the boat in regard to energy savings. And if you put those two in series, well, then now you're spending 200% of your energy cost, and really you could be spending 50% of that complete if the dryers has an energy saving potential. So there's things that we always talk about and try to explain to customers for different applications, but it's also a peace of mind because for them it may be, I have $1 million worth of product that's out there and I want to make sure that it's going to be clean and dry all the time. There are different ways that we can go about ensuring that the air treatment is always providing the correct pressure dew point, and if there's any alarms, indications, etc., that we can shut down different lines from redundancies. So, again, definitely like Justin said, CapEx, you could be spending more money than you need, especially if you've been, for lack of a better term, burned before, where you had a refrigerated dryer in the system, and maybe that refrigerated dryer wasn't sized for summer conditions, and all of a sudden you get water down the line, and the knee-jerk reaction is say, I'm getting rid of that refrige dryer and I'm putting in a desiccant, and I'm going to make sure that I don't have any moisture and my production's fine. Well, again, the CapEx, you're spending more money on the desiccant dryer, and then operating costs, you're spending more money on that as well. There are things too, like maybe you have a paint booth and that's not what you normally, that's a small portion of what you run. Well, you can have a point of use desiccant dryer for that. And then run the rest of the facility on a refrigerated dryer. So there are different things that we can do for various compressed air systems to save energy, save money, and then still build a system that's reliable for the customer for their needs.
Well, you both have outlined some of the challenges when it comes to issues of too much or too little air treatment. So Neil, let me ask you a question about pressure, if I could. What tips can you share with our listeners about how to tell if their system is running at too high a pressure?
So, yeah, I mean, normally speaking, one of our favorite things to do when we walk into a facility is to talk to folks, not just maybe our contact, which might be the maintenance manager, production manager, plant manager, but to talk to the folks that are operating the equipment. What's that minimum operating pressure you can run at? And it's almost like that telephone game we played as kids. I'm going to tell you one thing, and then let's see what happens down the line if everyone has the same answer. And truth be told, it's usually nominally, within a standard deviation, if you would, of what you would expect. But it differs. I may talk to the plant manager. They may say, "Oh, it's 125." Well, you talk to the operator, and he says, "If I go below 83 pounds, I have to scrap everything that I'm working on with this particular machine." And 83 pounds and 125 psi, that's a big difference. So the higher you run in operating pressure, the more you're going to make your equipment work. So typical air compressor is 80 to 125 psi operating, and you can buy compressors that have different air ends and so on, and you can run at higher pressures for different applications. But the higher you run, the more energy that compressor is going to expend, and the closer you're running to its utilization rate or service factor. Those compressors should be able to run there, but nonetheless, you're going to be paying more for it. At higher pressures, you will also have higher flows. So every use that's out there, if it's unregulated, is going to use more air if you're running at a higher pressure. So if I was able to run the entire plant at, say, 90 pounds, I'm going to have a significant savings running at 90 pounds than I would 100. And that's that artificial demand. The interesting thing with artificial demand is that all your tools, they may seem like, let's say you have an impact, my impact runs better at 120 pounds. Well, it will, but it's not going to run as long as it would if you were running at 90 pounds. So, the longevity of the tools, you're going to have to replace those pieces of equipment faster. So those are some other hidden costs that you might have. The neat thing that you can do these days is if you have a master controller, which has all your pieces of equipment, all your compressors on really one pressure setting. So you have most people say, oh, it's a glorified pressure gauge. Well, that's true. Really, you can see, it's 98 pounds right now, 98.3. Oh, it's 97. What's going on? But it gives you an opportunity to drop that pressure 1 psi at a time. So what we usually tell operators is once that master controller is in, start dialing that pressure down 1 or 2 psi a week, and then see what happens. Usually you'll have an operator or somebody say, oh, well, that's too low. And then oh my gosh, you know what? We were running at 125 pounds before, and now we're running at 95. We're saving, for every 2 psi reduction, we're saving 1% energy, and that's pretty huge. The other thing too is that you will have a pressure drop between the operation or the generation of the compressed air and that point of use, and that's an interesting point that I think most people don't think about is how do I make sure that if I'm operating in the compressor room at 95 that I get that out at the point of use. So that's one other thing that we have to take into consideration. That's that distribution network.
Okay, well, Justin, if I could target the next question at you, how would compressed air pressure specifically affect air quality?
Yeah, Tom. So, compressed air dryers are sized based on pressure and temperature, and the filtration is usually sized based only on pressure. So, if your pressure goes up, the capacity of your air treatment goes up. So, when plants say they need more pressure and they ramp up their compressor, this leads to the air treatment have more capacity. So, yep, you're going to have an insurance that your air treatment is going to work well because you're increasing the capacity of the equipment. But as Neil said before, whenever you turn up the pressure, you're going to increase the cost. The rule of thumb is for every 2 psi increase, correlates to about a 1% increase in energy costs. So as Neil said earlier, you do need to have the pressure at the lowest possible amount just so you can save some money. And some of your pressure problems could be due to poor distribution, undersized air treatment equipment, or even lack of maintenance. So in cases of facilities that are using more compressed air than their air treatment is capable of successfully treating, you're going to have contamination in the form of solid moisture or oil, and that can end up at the point of use. So, one way to avoid this is you can install an air main charging valve. This valve operates based on maintaining operating pressure on the compressed air generation side of the system. So this will ensure that you're getting your proper air quality and you will protect the air treatment equipment. So stable pressure at the point of use is also critical. So adding, FRLs to maintain that pressure is also beneficial.
Yeah,
Neil, your thoughts on Justin's response?
Yeah, Justin's points were fantastic. When it comes to air quality and operating pressure, one thing that we do stress is velocity in the piping. When we talk about expanding systems, and maybe we have a 50 horsepower today, and now we're adding another 50 horsepower to the system. What's that distribution pipe network? Is that distribution pipe going to be able to handle the additional flow without, let's say, considerable pressure drop? And what ends up happening is most folks overlook that or aren't aware that that could be a problem. And now we have, let's say, 500 CFM going through a system that we expected 200 CFM. So the velocities, as Justin mentioned, they could be relatively high, and that means that we don't have enough contact time for air treatment. And it also means that as we get faster in the distribution network, over 30 feet per second, then we start to see turbulence effect going on. And so normally speaking, when we're talking about drops and points of use, as you go faster, you're going to be potentially pushing, if there's any liquid water in the system, which it certainly could be if you have high velocities, you're pushing that water down to the point of use. So those are things obviously we would like to avoid. So that's what we say. And when you design the system, you're looking at 15 feet per second in the compressor room, 30 feet per second in the distribution piping, and 45 feet per second at the point of use. And that can really help ensure that you have the air quality that you started with, right? Because we're designing the system, we're making sure that everything works, but that piping aspect is really important.
Okay. Well, speaking of piping, let's close out today's podcast by considering piping further. I read an article recently about how that piping itself can affect the quality of the air. Can you talk a little bit more about how that works?
Yeah, sure. The material type of the piping can make a difference. Number one, we're always looking at a leak-free system. When we install something, we want to make sure that once it's up and running, pressure tested, holding pressure, that it holds pressure indefinitely. One of the interesting things for me is that over time, when we look in a compressor room, we may have a mixture of equipment manufacturers. Maybe we're adding equipment, like we have an expansion in the plant, so we need more compressors or more dryers, and so we may have a mix match of equipment, and that's fantastic, but we may not be upgrading that system piping. We go into plants and we see piping that may be endemic from the startup of the facility, and some of these facilities are 30, 40, 50 years old. I've seen certainly some receivers that are older than I am, which as long as you're having the inspections done, that's necessarily fine. But I think the thing that we tend to forget is that it's typically the low cost materials that are being installed, and so you see some black iron, you see some galvanized, and those tend to rust and scale. And so if we have that issue we just talked about with velocities not being considered, pressure drops not being considered, so if you have moisture coming out, that can start to degrade the pipe internally, and then you get rust and scale buildup, and you have significantly more pressure drop. which, like Justin and I both said, it's going to increase your overall operating costs. But the biggest things for customers is production. And, now if you use, let's say, call it inferior materials or materials that are going to rust and scale, now you're going to have the potential at that point of use, and then you're going to have a higher scrap rate or more downtime because now you have production equipment that is affected. So that's really, I think, the biggest thing for me. Copper, stainless steel, aluminum, those are really the best materials to choose for ensuring air quality in your system. And the other thing too is that I mentioned regulated uses versus unregulated uses. Having a master controller is a great way to do that, but you can also put in a flow controller to maintain system pressure downstream, or really at points of use, depending on how big those demands are. And that can also help with maintaining the operating pressure as low as possible, and potentially not affecting this air quality situation that we had in regard to the piping.
I think that wraps up today's episode on the hidden cost of compressed air. Let me once again thank both Neil and Justin for being here. Thanks, guys.
Yeah, thanks for having us, Tom.
Tom, always a pleasure to talk with you. Under Pressure always reminds me of David Bowie, so I'm getting my music on again, but very exciting.
We'll see if we can add that as the fade out music for today's episode, Neil.
Fantastic.
The next and final episode in this series will cover how to reveal and control costs with system monitoring. And if you like this episode, you can listen to the first 2 podcasts in the series, and those focus on the hidden cost of oversizing your compressed air system and the difference the system location can make to your bottom line. Once again, thanks to our speakers today, thanks to our sponsor, Kaeser Compressors, and thanks to you for listening.